All right. Good morning. Let's get down to business, guys. Let's do some stuff with the stuff about an Atwood machine, right? And it normally just looks like this, right? For our purposes, like when we talk about Atwood machines, it's going to normally look like this. And a real life example would be an elevator, right? You have some sort of cabin right here with some people in it. Got old Jim and Josie. I'll give her hair. Jim and Josie sitting in the elevator and they want to go up. Well, there's really one easy way to do that. And that's you attach a bunch of counterweight that weighs more than them. So if this has more mass than this, our counterweight's going to go down, and Jim and Josie are going to go up. Does that make sense? That's good. That's like the very basic. When we talk about, you guys know the word simple machine? That's a simple machine. I don't know if you guys did that in middle school or not. Like made simple machine projects or anything like that. But yeah. So that's a simple machine right there. But we use this a lot in physics, and you use this a lot more than you actually know. A lot of things run off of this principle. So let's talk about this for a second. Let's think, what are the forces acting on these sort of objects right here? So Ethan, what kind of force is the elevator feeling?
Gravity.
Yes, gravity. Force of gravity. There's actually one other force on the elevator. Ethan and Grayson, do you guys think you can figure it out? Do you guys think you know?
The force of the counterweight.
Yes, the force of the counterweight, but it's not the counterweight. What is it? It's the counterweight has a force of gravity also. You're right. So what is the counterweight doing? In the most basic terms, like if you asked a 3-year-old what the counterweight is doing, what would they say?
Pulling it up.
Yes, it's pulling it up. So this is going down and that's going up. So what then is this cable attached to the elevator? What kind of force, what direction is that force pointing? It's pointing up, yes. It's called tension, right? There's a force of gravity trying to push down on it, but the tension is pulling up. Conversely, which direction is the tension for this counterweight? The tension's down?
Possibly.
Which way do you think the tension actually is? Let's actually look at these examples right here. Let's go over here to our pulleys that we have set up right here. What is the direction of the tension? Here's our normal weight right here. Grayson, can you help me out with this?
Yeah.
You come over here too. Let me come around here and film it like this. All right, get in there. All right, let's see. Now, we already said that the tension from this is coming up like that, right? And there's gravity pushing down. Here's our counterweight. All right, what direction is the tension on the counterweight? You guys could do it. It seems like a trick question, but it's not. It's not a trick question.
Down.
It's not down.
Up.
It's up. Why is it up?
Because that's where the pulley is.
Right. Yes, this pulley is like the center. So like the tension is still up. Like this is still being pulled up by the rope, even though it has a counterweight that's trying to go down. Does that make sense?
Mm-hmm.
So if you let go of it, you just let go of it. It goes down, and our cab goes up.
Well, that was for the lighter side. The counterweight was the other side.
I didn't realize it was a trick question. It's a trick question.
It's a trick question.
It's a trick question. Yeah. Okay, so now, if we really talk about this, now the overall direction of this machine, which direction is the rope spinning? Is it spinning this way or is it spinning that way? This or that? That. Yes, it's going that way. Right, this is being pulled up and that's being shot down, even though it still has tension upwards because of the pulley. Make sense? Now, we write this, and there's a formula for this, and you can talk about it like this, and you write the acceleration of whatever object you're looking at, okay? The acceleration is equal to gravity times mass 1 minus mass 2 over mass 1 plus mass 2. All right? It's not scary at all, right? I'll give you two masses. I'll say 35, 20. You just subtract it and add it, and multiply it by gravity, and that's your acceleration. That's it. So it's really simple like this, and let's do a question example right now. So let's say, old Jim and what was her name again? Josie? Josie. Jim and Josie, they weigh an astounding 650 kilograms. Just real Midwesterners, that's a joke. And then, that's a bad joke. Just corn dogs and cheese and sweet tea. 650 kilograms. And our counterbalance, 700 kilograms. I'm getting close to 650. Not even. This is mass 1. No, we'll call this mass 2. It's mass 2, and this is mass 1. So let's do this together. We want to find the acceleration of this car going up. So our acceleration is then going to equal g, which we know is gravity. What do I put in for mass 1?
700.
Yes. What do I put in for mass 2?
650.
Yeah. I'm treating you guys like kindergartners.
Where?
What color is this?
Red.
Purple. Alright. And now we just add it at the bottom. Okay? And then we use our calculators here. 700 minus 650, that equals 50. 700 plus 650, that's, I don't know, 1350. So really we get A is equal to G times 50 over 1350 divided by 1350 equals times 9.8. So then we get an acceleration. It's equal to 0.36 meters per second squared for mass 2. For our mass 2, our acceleration is going 0.36 meters per second squared up. How about this question? What's the acceleration of the counterweight? Is it going to be faster or slower?
Faster.
You think it's going to be faster?
Maybe.
What are your thoughts?
This
is actually a trick question.
Oh, it's the same.
Mm-hmm.
Would it be the same because they're pulling?
Yes. Remember, because the tension is the same, right? The tension of the rope. So the counterweight can't go faster than the elevator. The elevator can't go faster than the counterweight. What's the only thing that changes? There's only one thing that changes.
Direction.
The direction. And how do we write direction when we talk about vectors?
Arrow down.
Yes. Or a negative sign. So if this elevator has positive 0.36 meters per second acceleration up, right? And if up is the direction we want to go, then our counterweight is going negative. It's going down. It's bad. 0.36 meters per second squared. Let's do it. Let's go back here to these pulleys and let's try this. And you guys can tell me the acceleration, and then we'll actually measure it with a meter stick and see if we were right.